Hey there, welcome on a video on section 5.4 on factoring and solving polynomial equations. So this should be some review from the previous unit, but we are going to be dealing with some polynomials that are bigger than degree 2. So let's start with number 1. So usually whenever you see 4 terms, typically you're going to want to do factor by grouping. And in case you forgot factor by grouping, we usually group the first 2 and the last 2 terms. And in fact, what we could do is look at our flow chart from a while ago. Hopefully you still have it. If not, I can print some for you guys. Probably have it over here under chapter 4. There we go, factoring flow chart. So yeah, 4 terms, you're going to want to do factor by grouping. So we'll refer to this when we need to. And then you factor out a common factor from each group. So we can factor out x squared. Actually, we'll do a negative x squared, so it comes x minus 1. Then if you can factor from the second group, so you can just put a 1 on the outside, because anything times 1 is itself. And then, of course, x minus 1 times 1 minus x squared. But we want to factor it completely. This can be a difference of 2 squares, 1 minus x, 1 minus x. So that's how that one's done. Now we have 3 terms. Going back to the factoring flow chart, we want to take common factors out. So that's what we're going to do here. We see that 4y squared is a common factor. We get y squared minus 4y plus 4. Then we see that the first and last terms are perfect squares, and it does factor as a binomial squared. So it's going to be y minus 2 times y minus 2. Or if you so desire, you can write 4y squared, y minus 2 squared. Either way works. We have 2 terms. We look for common factors, which I don't see there. But it does represent a difference of 2 squares, because 16 and 81 are both perfect squares and there's a minus in the middle. So it's 4x squared minus 9 and 4x squared plus 9. Then factor the 4x squared minus 9 further, there's 2x plus 3, 2x plus 3. But there's no such thing as a sum of 2 squares, because that just really is what it is. They can't really break that down any further. But it's difference of 2 squares. We have the luxury of breaking down, as we see right there, a minus b times a plus b. Now, why is this important? Why are we doing factoring? Well, if we take a look at number 2, there's some purposes of factoring. One purpose is to solve for x-intercepts. Or actually, let me rephrase that. We'll just say solve equations. Another purpose is to find x-intercepts on a graph. And also for simplifying expressions. Those are 3 purposes for factoring. So it's a very essential technique as we move on to more advanced math skills. That's why we're reviewing this here. So obviously, number 2, we're going to solve an equation. And we were saying the equation equal to 0. And actually, we just factored this earlier in number 1, part A. I could just simply rewrite the factored expression right here. Well, that was a plus right there. And then all you're doing is setting each factor equal to 0. So this is called a zero product property, which basically means anything times 0 equals 0. So anything times 0 equals 0. This helps to solve equations by factoring. That's why we have it. So we factored it, and we see that we have a bunch of factors being, of course, multiplied together. So if I set each factor equal to 0, using the zero product property, I can get the answers. I get 1, 1, and of course negative. Later on, we'll actually start using this to help us with graphing. We'll do that later in this unit. More solving by factoring. So there's actually 4 examples here. I'll do A and C, then I would ask you guys maybe pause the video and do B and D, and we'll see if we get the same answers. But for A, what you want to do is get everything on the same side first, and try to write it in standard form, like the exponents is going in descending order. So I'll factor out 3x, I get x4 minus 6x squared plus 5. 3x, x squared minus 5, x squared minus 1. And we have something like x4, you can actually break it down as x squared, and treat it like a quadratic. Obviously, it's not quadratic, but you can treat it that way so you can make the factoring easy. And if you set each factor equal to 0, you get x equals 0 for this one. This one's going to be plus or minus root 5, because it is x squared. And that one's going to be plus or minus 1. So thus we get 5 answers for that one. Put the one down below. Again, same thing. You got to move everything over to one side first. Very, very important. And factor out 2x. x4 minus 7x squared plus 12. You're just going to kind of do the same thing. We're going to factor even further. x squared minus 3 minus 4. X is 0 plus minus root 3, and of course plus or minus 2. So we get 5 answers again. So go and pause the video. I'm going to work out B and D and see if we get the same answer. Okay, hopefully you got the same answers. Notice for D, we only had 3 answers instead of 4 answers, even though we had degree 4. The x squared obviously got a 0. We're going to say that has a multiplicity of 2, and we're going to talk about that later in this unit, but I just want to at least briefly discuss that right now. So again, we see the main purpose of factoring, or one of the purposes, is to solve equations, which we just did. We actually did several equations that were solved by factoring. And if you actually were to graph these, then these would actually be x-intercepts as well. And you could also use it to help you simplify expressions. If you had, like, say, a polynomial on top of another polynomial you wanted to simplify it, if you have common factors, you can cross them off. So, and of course, we're using the zero product property here to get this done. Okay, let's look at a few more. So, sketching a graph. Actually, we just did this one in part B, so I don't need to do it again. So, it was y equals 4x. It was x squared minus 1, x squared minus 9. So the zeros of x-intercepts were 0, plus or minus 1, plus minus 3. So I'll do a little coordinate plane here. The y-intercept is 0 because we don't see one. We don't see a constant. And of course, it's an x-intercept as well. 1 and negative 1, 3 and negative 3, And we know the end behavior is going to have to be down up. Remember, our degree is odd, leading coefficient is positive. So it's going to look kind of like this. It's going to have several turning points. So there we go. Now, how high or low some of these portions of the graph go, we don't know. And that's because that requires some calculus, which we won't worry about until a couple years from now. Multiplying stuff out, we did 5.3. That's like 5.3 review. But you can see why we're going to do this when we get to this stuff down here. So if I were to distribute the A to each of those three terms, distribute the B to each of those three terms, you're going to wind up getting this A cubed minus A squared B plus AB squared plus A squared B minus AB squared plus B cubed. But you're going to notice that several terms will cancel, leaving us just A cubed plus B cubed. If I do likewise for part B of this example, I get A cubed plus A squared B plus AB squared minus A squared B minus AB squared minus B cubed. Again, lots of things cancel. You show up with A cubed minus B cubed. Now, when you have A cubed plus B cubed, we call that a sum of two cubes, clearly because we're adding two cubes. And actually, since we just got A cubed plus B cubed from foiling number 5, part A, we actually can say that A cubed plus B cubed can be factored in this fashion. And that's going to be a formula that I'll probably give to you guys. I won't expect you to memorize, but this is a way to factor a sum of two cubes. There's two cubes just in 5 part B. So whenever you have two perfect cubes being subtracted like this, it can be factors A minus B times A squared plus AB plus B squared. And again, we just had proved that A cubed minus B cubed equals that expression by the foiling that we did in 5 part B. So let's put this in practice. So x cubed plus 64 is, well, actually, first we're going to say this. A cubed is x cubed, B cubed is 64. That means that A is x and B is 4, because those are the cube roots of x cubed and 64 respectively. So now if I apply the formula, A plus B times A squared minus AB plus B squared, I'm going to replace A with x, replace B with 4, and then replace A with x again, minus 4x plus 16. Again, A cubed is W cubed, B cubed is 27, A is W, and B is 3. W minus 3, W squared plus 3W plus 9. That's just using the difference of two cubes right above. And likewise again, 8 and 125 are perfect cubes. A cubed equals 8x cubed. So A is 2x. B cubed is 125. The cube root of 125 is 5. You get 2x minus 5. And then if you plug in 2x into A, that's 4x squared plus 10x and plus 25. And you can actually prove it by distributing the 2x and negative 5 into the 4x squared plus 10x plus 25 expression to see if you do get 8x cubed minus 125, and we would. So we'll practice these problems when we meet again as a class, and then use these skills to help us do graphing and solving some rather long polynomials. Okay, looks like we're all set. Oh, one other thing, as I mentioned earlier in the video, there's no such thing as a sum of two squares, because 4x squared plus 9 cannot be factored, but we do have a sum of two cubes. So sum of two cubes exists because that can be factored, but not sum of two squares, and that actually will be a follow-up question in the Google form. And lastly, just make sure you guys are paying attention. Siri is watching football this weekend. That's how I'm spending my weekend. And There is a game going on, but I decided to take a little break from it so I can make this video. All right, I'll see you guys on Monday. Bye.